For decades, every exoplanet we knew about was invisible. We never saw them. We only saw their fingerprints. A flicker of starlight, a tiny dip in brightness, a wobble in a star's motion. Astronomers built an entire universe of hidden worlds out of shadows and math. And then the Kepler Space Telescope did something almost unthinkable. It didn't just detect another world, it captured the closest thing to an actual image of one. To understand why that matters, you have to understand how starved scientists were for anything resembling real proof. Exoplanets are absurdly small compared to the stars they orbit and absurdly far away. A planet like Earth, seen from a neighboring star system, would be a speck of light drowned out by the blazing furnace right next to it. Even with the most powerful telescopes ever built, actually, photographing a small, rocky world orbiting another sun was considered close to impossible. So for years, the entire field of exoplanet science ran on indirect evidence. Kepler's own method was built on that limitation. It stared at the same patch of sky, watching more than 150,000 stars at once, waiting for the smallest possible dimming when a planet crossed in front of its star. That dimming, sometimes less than 1/100%, was the only clue Kepler needed. It was brilliant. It was also, in a strange way, blind. Kepler never saw a planet directly. It saw a shadow of a shadow, a mathematical signature buried in a wall of light. That is what makes this moment so different. Deep inside years of Kepler's archived data, sitting in the numbers long after the mission itself had gone quiet, researchers found something nobody expected to find in a transit survey. Not just a signal, not just a dip in brightness, a reconstructed visual, built directly from the telescope's own light measurements, detailed enough to actually resolve the silhouette of a world crossing in front of its star. For the first time, instead of inferring a planet from a graph, scientists could look at something close to a picture. A dark curve sliding across the face of a star, sharp enough to estimate its size, its shape, even hints about its atmosphere bending the starlight at its edges. This was not a snapshot taken by a camera in the way people imagine a photograph. There is no lens on Earth or an orbit powerful enough to zoom in on a rocky planet trillions of miles away and capture it the way you'd photograph a mountain range. What Kepler's data allowed instead was something almost more remarkable. By combining an enormous number of individual light measurements, each one capturing a fraction of a second of the planet's transit, researchers were able to stack, align, and reconstruct an image-like profile of the object itself. It is the closest thing humanity has ever produced to a real picture of a world beyond our solar system, built not from a single click of a shutter, but from thousands of precise measurements stitched together into a shape. And what a shape it turned out to be. The world in question sits far closer to its star than anything in our own solar system dares to orbit, completing a full year in only a matter of days. Its size falls somewhere between Earth and Neptune, in that strange category astronomers call a sub-Neptune, a type of planet that does not exist anywhere in our own solar system, yet appears to be one of the most common planet types in the galaxy. The reconstructed transit shows something scientists did not expect. Subtle asymmetries in the light curve, tiny variations that suggest the planet's atmosphere is not uniform. Instead of a clean, perfectly round shadow, the data hints at something messier, an atmosphere with structure, with layers, possibly even with weather. That single detail changed how researchers talked about the discovery. A shadow is just a shadow. But a shadow with texture is a world with a story. Weather implies motion. Motion implies energy. Energy implies a planet that is not just sitting there dead and static, but doing something. Reacting to its star, cycling through temperature changes, possibly even hosting the kind of dynamic atmospheric chemistry that scientists look for when they search for signs of a living, breathing planetary system. To be clear, nobody is claiming this world is habitable. Sitting this close to its star, it is almost certainly scorching, more likely to resemble a slow roasting furnace than anything resembling Earth. But that is not really the point. What makes this moment stand out is the contrast with how exoplanet science used to work. Go back 20 years, and the entire field survived on faith in numbers. A star dims by a fraction of a percent, an algorithm flags it, a team of scientists spends months confirming it is not noise, not a star spot, not an instrument error. Then a paper gets published, a name gets assigned, and the planet exists only as an entry in a catalog. No image, no shape, nothing your eyes could actually process. For most people outside astronomy, that abstraction made exoplanets feel distant in more than one sense. Hard numbers on a chart do not stir the imagination the way an actual picture does. This reconstruction changes that emotional distance. Suddenly, there is something to look at, something with an outline, something that starts to feel less like a statistic and more like a place that could be visited, at least in theory. The point is, what this discovery proves is now possible. If Kepler's old data, gathered years ago with instruments designed only to measure brightness dips, can be reprocessed into something this close to an actual visual reconstruction, then the entire archive of exoplanet data suddenly looks different. Every star Kepler ever watched, every transit it ever recorded, becomes a potential source of new image-like reconstructions. Worlds that were once just numbers on a spreadsheet could start turning into shapes, silhouettes, maybe even hints of texture and atmosphere. This is where the story stops being about one planet and starts being about a method. For years, direct imaging of exoplanets was reserved for a tiny handful of extreme cases, enormous gas giants sitting extremely far from their stars, young and still glowing with leftover heat from their formation. Those planets were essentially bright enough and separated enough from their stars that telescopes equipped with specialized instruments could block out the starlight and catch a faint dot of the planet itself. But that method only worked for a rare category of world: small, rocky, close-orbiting planets. The ones most likely to matter if we are searching for life, were considered completely out of reach for anything resembling direct imaging. What Kepler's reconstructed transit data suggests is a workaround. Not a photograph in the traditional sense, but a mathematically rebuilt image, precise enough to reveal shape and structure for exactly the category of planet that direct imaging telescopes struggle to touch. It also raises an uncomfortable, thrilling question. If old Kepler data, sitting untouched for years, could hide something like this, what else is buried in there? The Kepler mission produced an almost unimaginable volume of data across its 9 years of operation, watching hundreds of thousands of stars, recording brightness measurements over and over, day after day. Only a fraction of that has ever been fully mined with modern techniques. Every year, computing power increases. Every year, the algorithms used to process light curves get sharper, more sensitive, better at pulling structure out of noise. That means the Kepler archive is not a closed book. It is a slowly reopening one. This newly reconstructed world may not be the last. It may just be the first proof that these kinds of reconstructions are even possible. Newer telescopes are watching closely. James Webb was never designed to take pretty pictures of small rocky exoplanets either, but it has already shown it can pull atmospheric fingerprints out of starlight with incredible precision, detecting individual molecules drifting in the air of worlds trillions of miles away. If Webb's atmospheric data can eventually be combined with reconstruction techniques like the ones used on this Kepler discovery, the two methods together could produce something astronomers have wanted for decades. Not just a shape, and not just a chemical signature, but something that starts to resemble a real, detailed portrait of another world. Its size, its structure, its atmosphere, maybe even its weather, assembled piece by piece into something that finally looks less like a graph and more like a place. There is something almost poetic about where this discovery came from. Not a brand new telescope, not some futuristic instrument built specifically for this purpose. It came from data Kepler collected years ago, sitting quietly in storage, waiting for the right techniques to catch up to it. The telescope itself went dark back in 2018, its fuel exhausted, its mission long since declared complete. And yet here it is, years later, still producing firsts, still reshaping what scientists thought was possible. It turns out Kepler's real legacy was never just the thousands of planets it confirmed while it was active. It was the depth of the archive it left behind, a dataset so enormous that we are still finding new ways to ask it questions. There's also a practical side to this that rarely gets talked about outside research circles. Reconstructing an image-like profile from transit data is not cheap in terms of computing power. It requires combining thousands of individual measurements, correcting for noise, filtering out contamination from neighboring stars, and running models that simulate how light bends and scatters as a planet crosses in front of its star. A decade ago, the computing resources needed to do this kind of reconstruction at scale simply did not exist in any practical, affordable way. Today, the same techniques used to sharpen blurry photographs or clean up old film footage are being adapted for astronomy, letting scientists pull far more detail out of old datasets than the original instruments were ever designed to deliver. That shift alone means missions like Kepler are effectively becoming more valuable with time, not less. Every improvement in computing and modeling adds a new layer of detail to data that has already been sitting in storage for years. For most of the history of exoplanet science, the goal was simple: find them, prove they exist, count them. Kepler did that job better than anyone could have imagined, confirming thousands of new worlds and reshaping our understanding of how common planets are across the galaxy. But finding a planet and understanding a planet are two very different things. This new reconstruction pushes us from the first category into the second. It is not just proof that a world exists, it is the first real glimpse of what that world might actually look like. We are still nowhere near the point where a telescope beams back a crisp photograph of an alien landscape, the kind of image you might imagine from science fiction. That technology, if it ever comes, is likely still decades away, But the gap between having nothing but numbers and having something that resembles a real image just got smaller than anyone expected. A silhouette with texture, a shadow that hints at weather, a shape pulled out of years-old data by techniques nobody had when that data was first collected. That is the real story here. Not that we suddenly have a photograph of another Earth. We do not. But we have proof that the tools we already have, the missions we already flew, the archives we already own, are capable of producing far more than we ever expected. Kepler was never built to take pictures, and yet, in its own quiet way, it just took the closest thing to one that humanity has ever seen of a world beyond our solar system. If this is what old data can still reveal, imagine what is still hiding in it, waiting for someone to look at it the right way. The next reconstructed world might be closer to Earth than this one. It might sit in the habitable zone. It might show the kind of atmospheric texture that makes scientists sit up and pay very close attention. Somewhere in those hundreds of thousands of stars Kepler once watched, there could be dozens of other worlds waiting for the same treatment, waiting for someone to run the right algorithm, apply the right correction, and pull a shape out of the noise. Kepler already changed how we search for planets once. It may be about to change how we actually see them.